Good afternoon.
Good afternoon.
Yesterday, we just thermometry. Today we can see expansion of that solids. Now, basically, solids have definite shape and size. On heating the solid, its length, area, and the volume may change. So we define three coefficient of expansions for that solids. That we know that alpha, beta, and gamma. This is coefficient of linear expansion, coefficient of linear expansion, coefficient of aerial or superficial expansion. Gamma means coefficient of cubical or volume expansion. Cubical or volume expansion. So that is alpha, beta, and gamma we can define for solids. And we know that alpha can be defined as change in length by its original length or unit rise in temperature. Change in length by original length per unit rise in temperature. That is delta L by L delta theta. Or we write it as L2 minus L1 by L1 into T2 minus T1. Or theta 2 minus theta 1. Instead of that delta theta, we can use delta T. Here we can assume theta minus T1, T2 minus T1 degrees Celsius. So alpha we can define it as change in length by original length or unit rise in temperature. And beta can be defined as delta A by A into delta T or A2 minus A1 by A1 into T2 minus T1. And the cubical expansion we may define it as change in volume by original volume or unit rise in temperature. Or V1 and V2 are the volumes of the solid at T1 and T2 degrees Celsius. So we write gamma as V2 minus V1 by V1 into T2 minus T1. And here, final length of the rod. Final length of rod or object. L2 can be written as initial length into 1 plus alpha into T2 minus T1. They give at T1 degrees Celsius, the length of the object is given. At T2 degrees Celsius, length of the object we may calculate by using that relation from the alpha definition. And final area. Final area of that object we may write it as final area means area at T2 degrees Celsius that equal initial area into 1 plus beta into T2 minus T1. And final volume of that object we write it as V2 equal to V1 into 1 plus gamma into T2 minus T1 to the final volume. And the linear expansion. Linear expansion is nothing but change in length. Change in length. Coefficient of linear expansion means alpha. Just linear expansion means change in length. Change in length. It is delta L is equal to L1 into alpha delta theta or L alpha delta T. And aerial expansion. Aerial expansion or change in area. Change in area. Delta A is equal to A beta into delta T. And the volume expansion of object or change in volume or rise in temperature can be calculated as delta V is equal to gamma V delta T. Gamma V delta T. Here alpha, beta, gamma all are measured in per degree Celsius. Alpha, beta, gamma all are measured in per degree Celsius or per Kelvin. Per degree Celsius means degree Celsius inverse or Kelvin inverse. If you want to convert in Fahrenheit inverse, or if the alpha value measured in per degree Celsius is greater than alpha value measured in per degree Fahrenheit. Alpha value measured in per degree Celsius is greater than alpha value measured in per degree Fahrenheit. Means if we convert the alpha value given in per degree Celsius, if you want to convert into per degree Fahrenheit, we get less value. We get less value. Yesterday we see 1 degree Celsius interval equal to 1.8 degree Fahrenheit interval. 1.8 degree Fahrenheit interval. So we get less value if we convert in per degree Fahrenheit. Means alpha value given in per degree Celsius is greater than alpha value given in per degree Fahrenheit. And for isotropic solids, isotropic means the expansion is same in all directions. Same expansion in all directions. We can say that solids are isotropic. Alpha is to beta is to gamma is 1:2:3. The relation between alpha, beta, and gamma is 1:2:3. Means beta is equal to 2 alpha, gamma is equal to 3 alpha. For anisotropic solids, based on this anisotropic solids given in last year mains, one question is given in last year, I think so this year mains, in January shift. For anisotropic solids, gamma is equal to or alpha average. Alpha average can be defined as alpha x plus alpha y plus alpha z by 3. Alpha x plus alpha y plus alpha z by 3 for anisotropic solids. Means gamma is equal to alpha x plus alpha y plus alpha z. That is 3 times of average alpha value. 3 times of that average alpha value. Gamma can be defined as for anisotropic solids alpha x plus alpha y plus alpha z. In the numerical type question, they give, I think so, they give alpha value in one direction and other two mutually perpendicular directions give some alpha value. Means if suppose if we can take alpha x as 2 into 10 power minus 6 and alpha y and alpha z is given as some 3 into 10 power minus 6. Then gamma value they need to calculate. Gamma value they want to calculate. So in one direction alpha value they give, in other two mutually perpendicular directions, they assume that these two are equal. Other two mutually perpendicular directions, these two are equal. So alpha y and alpha z we can substitute that value and alpha x we can substitute. From that we can calculate the gamma value. And similarly beta is equal to 2/3 of alpha x plus alpha y plus alpha z. It is 2/3 of that 2 times of that alpha average. Alpha average is given as alpha x plus alpha y plus alpha z by 3. So we get 2/3 of alpha x plus alpha y plus alpha z. That is in case of anisotropic solids, and this is for isotropic solids. So based on these relations, now we are going to see some models. Now, if suppose important model, frequently asking question. Two rods of length L1 and L2. If two rods of length L1 and L2 rods of length L1 and L2 having coefficient of linear expansions alpha 1 and alpha 2. Coefficient of linear expansions alpha 1 and alpha 2 have same difference in lengths at all temperatures. The two rods have same difference in lengths. If two rods have same difference in lengths, at all temperatures, then same difference in length, we can say some x at all temperatures. Then x value we need to find, and L1 and L2 value, length of that each rod we need to find. And condition for that. And what is the condition? For which the two rods have same difference in length at all temperatures. So here the difference in length at T1 degrees Celsius, we can assume at T1 degrees Celsius, we can assume the difference in lengths of the rod, we can take it as some x. At T2 degrees Celsius also, at T2 degrees Celsius, the length of the each rod changes, but still the difference in length should be same. The still difference in length is same. Then condition for that. What is the final length of the rod? Where L1 and L2 are the length of the rods at higher temperature. L1 and L2 are length of the rod at T1 degree Celsius. T1 degree Celsius. Therefore, L2 dash can be written as L2 into 1 plus alpha 2 into T2 minus T1 minus final length of the rod can be written as initial length into 1 plus alpha 1 into T2 minus T1, which is equal to x. Now L2 minus L1 is equal to x. That term should be cancelled out. Therefore, L2 minus L1 plus L2 alpha 2 minus L1 alpha 1 into T2 minus T1 is equal to x. These two terms get cancelled because L2 minus L1 is equal to x, and that equal to 0. Therefore, L1 alpha 1 is equal to L2 alpha 2. This is the required condition for the difference in length should be remains same, or L1 by L2 is equal to alpha 2 by alpha 1. In the exam, they give alpha 1 and alpha 2 values. Therefore, the ratio of the lengths chosen such that the difference in length is same at all temperatures. The difference in length is same at all temperatures. This is the first condition. And second one, they give x value in the data. We need to calculate the length of that each rod. As we know that L1 alpha 1 is equal to L2 alpha 2, and L2 minus L1 is equal to x. By using that L2 minus L1 is equal to x, and L1 alpha 1 is equal to L2 alpha 2, on solving, any doubt?
No, sir.
Now, on solving these two equations, we have to write L1 as L2 minus x. L1 as L2 minus x, so we get L2 value, and L2 can be written as L1 plus x. We get L1 value. So, which upon simplification, we get L1 as alpha 2 into x, by alpha 1 difference alpha. Difference means we don't know which is more. Alpha 1 is more or alpha 2 is more, we don't know. So we can take the difference. And L2 can be taken as alpha 1 into x by alpha 1 difference alpha 2. If alpha 1 is greater than alpha 2, we write alpha 1 minus alpha 2. This symbol is negation, means difference we can take. And in previous year, they give a question like this. What is the value of difference in length is same at all temperatures? What is the value of L1 plus L2 by L1 or L2? What is the value of L1 plus L2 by L2? That thing we need to find. So we get here L1 by L2 is equal to alpha 2 by alpha 1. By adding plus 1 on both sides, we get L1 plus L2 by L2 is equal to alpha 2 plus alpha 1 by alpha 1. So if we want to calculate L2 by L1 plus L2 value, we get it as alpha 1 by alpha 1 plus alpha 2. So out of these three results, any question they may give. So like this. L2 by L1 plus L2, we get alpha 1 by alpha 1 plus alpha 2. If you want to find L1 by L1 plus L2, we have to take reverse this. L2 by L1, we write it as alpha 1 by alpha 2. L2 by L1, we write it as alpha 1 by alpha 2. So here you get alpha 2 term. L1 by L1 plus L2 is equal to alpha 2 by alpha 1 plus alpha 2 you get. Two rods of length L1 and L2 made up of different material form the composite rod. Two rods will form the composite rod. One is made up of length L1. One is of length L1 and made up of material of linear expansion alpha 1. Another one is of length L2 having coefficient of linear expansion alpha 2. So this composite rod formed at T1 degrees Celsius. At T1 degree Celsius. This is a composite rod. Means the two rods are riveted together and joined together, forms a single rod. If the temperature is increased to T2 degrees Celsius, so if temperature of rod increased to T2 degrees Celsius, the increase in length of composite rod. Increase in length of composite rod and alpha value for that composite rod. Alpha for composite rod. So here at T1 degree Celsius, the composite rod is having length L1 plus L2 and having linear expansions alpha 1 plus alpha 2. So due to change in temperature, what is the length of the change in length of the rod? Increase in length of composite rod. L1 dash plus L2 dash minus L1 plus L2. L1 dash plus L2 dash gives L1 dash means L1 into 1 plus alpha 1 into T2 minus T1 plus L2 dash means L2 into 1 plus alpha 2 into T2 minus T1 minus of L1 plus L2. So first term get cancelled. Here we have L1 plus L2. Here we have minus of L1 plus L2. So which upon simplification L1 alpha 1 plus L2 alpha 2 into T2 minus T1 is the change in length or increase in length of the rod, composite rod. L1 alpha 1 plus L2 alpha 2 into T2 minus T1. And from the definition of alpha, we can define it as change in length of composite rod by initial length of the composite rod into T2 minus T1. From the alpha definition, change in length by original length into change in temperature. Here delta L by T2 minus T1 we get L1 alpha 1 plus L2 alpha 2 by L1 plus L2. So this is the alpha average or mean coefficient of expansion of the composite rod. Mean coefficient of expansion of this composite rod.
సార్ ఒక్కసారి 1 minute చూపిస్తాను. Yes, sir, done, sir.
No problems in this. Here, two rods considered here, A and B. Consider two rods, A and B. So the length of first rod it is given as some 25 centimeter, and the length of second rod it is given as some 40 centimeter. So when the temperature changed to temperature is increased by rod A temperature increased to 100 degrees Celsius, the length of the rod A, you can say LA and this is LB, is the initial length of the rods. And the change in length of the rod A it is given as 0.05 centimeter. And when the temperature of that rod B is increased to 100 degrees Celsius, change in length of the rod B, it is given as 0.04 centimeter. 0.04 centimeter. Now, the composite rod is made. A composite rod is made by using this. Composite rod is made by using this two rods by taking X part of that first rod and X part of that second rod. So composite rod is made. The length of this composite rod, see, it is given as 50 centimeter. 50 centimeter. So by taking the one piece of this rod A and another piece of that some part of rod B is taken and form a composite rod. Composite rod made of A and B. So we can say it is rod C. C made of A and B. So when the temperature of this composite rod increases to 30 degrees Celsius, then change in length of this composite rod is given as 0.03 centimeter. Then find the X and XB. And find the length of piece of A, B. Anybody want to try? Anybody? Or want to try?
Sir, tell sir.
Here actually, so according to that given information, the composite rod length initially 50 centimeter, increase in length of the composite rod is given. So that composite rod is made up of lengths, first and second rod, made up of that A and B. So the length of that piece of A, it should be XA, and the length of that piece of B, it should be XB. Then we need to calculate the XA and XB values. So first of all, from the given information, we can find alpha A and alpha B. From given information, they want to give diagram, total theory they give. So that's the information provided. Now from the given information, coefficient of linear expansion of that metal A. Coefficient of linear expansion of that metal A should be equal to, we can calculate delta LA by LA by delta TA. Delta LA, it is given as 0.05, and LA value, it is given as 25, it is 100, which upon simplification, 5 into 10 power minus 4, 5 by 25, 1 by 5, 0.2 into 10 power minus 4, we get 2 into 10 power minus 5 degrees Celsius inverse. And similarly, alpha B can be calculated as delta LB by LB into delta TB. Change in length of that B is given as 0.04, and the length of that B, it is given as 40 centimeter. Change in temperature is 100. Again, which upon simplification, 4 into 10 power minus 2, here 100, 1000 we have. So we get 1 into 10 power minus 5 degrees Celsius inverse. Alpha A and alpha B values we get. And for C, for composite rod, you can say C, what is the length of this composite rod? XA plus XB is equal to 50 centimeter. 50 centimeter. Then what is the increase in length? 0.03. So delta XA plus delta XB is equal to 0.03. When the composite rod expands means each rod will expand. Each piece of the rod will expand. Individual expansions delta XA plus delta XB. Delta XA we rated as XA alpha A delta theta C plus XB alpha B delta theta C. Because composite rod temperature is increased to 30. Don't write here delta A, delta TA. When the temperature of the composite rod is increased, delta XA means the increase in length of that part of this rod A. The increase in length of this part of this rod A, that is increase in length, we write as initial length, it is XA, alpha value alpha A into delta theta C is equal to 0.03. Delta theta C, it is given as 30 degrees Celsius. Alpha A, alpha B we calculate. Therefore, we get a relation between XA and XB. Or XB is equal to 50 minus X. XB is equal to 50 minus X. So solve these two equations. Solve these two equations. Do it fast. Solve 1 and 2. Delta theta C, you can substitute here 30 degrees Celsius. 30 degrees Celsius, we get XA and XB values. Values ఎంత వస్తాయో చెప్పండి త్వరగా క్యాలిక్యులేషన్. How much you get? Calculation ఎంతసేపు చేశారు? Yuvan, Kaushal, Saket, Natanj. Are you doing or not? Calculation.
Doing, sir.
Okay. Delta C given as 30. 0.03 by 30 means here we get 10 power minus 3. 10 power minus 3 and alpha A, alpha B, 10 power minus 5. Here we get 100, 2xa. 2xa plus xb we get 100 now. So xa plus xb 50 and 2xa plus xb 100. By subtracting 2xa is equal to how much? 50. You clear? XA 50 and question now. It's in the 25, 40 kada. So take it as some 50 degrees Celsius. Take it as 50. Delta C you can take it as 50. 50 means 0.03 by 50. 0.03 by 50. 3 by 5, 0.6 into 10 power minus 3. That is 6 into 10 power minus 4. So here we have 60. 2xa plus xb we get here 60. Take delta C is 50 degrees Celsius instead of 30. So you get 2xa plus xb, you get 60. Then by subtracting here, 2xa plus xb minus xa plus xb means we get xa is equal to 10 centimeter and xb is equal to xa 10 means xb 40. Only 10 centimeter of that rod A is taken and 40 centimeter of this rod B is taken and riveted as a composite rod or made up of composite rod. Is it clear?
Yes,
Now,
sir.
more important, 3 rods form the isosceles triangle. Isosceles triangle. These two sides are made up of material of coefficient of linear expansion alpha 2 and this side is made up of coefficient of linear expansion alpha 1 such that so rods are from isosceles triangle. These two sides equal, opposite angles are equal, and assume theta is constant. Assume theta is constant and altitude and height of the triangle is constant. Height of triangle is constant. So when temperature is raised by delta T, when temperature raised by delta T degrees Celsius, then find L1 by L2 value. L1 by L2. So here it is made up of composite rod, isosceles triangle. As when the temperature increases, all the rods expands. All the rods expands. All the rods expands. all the rods expands. Now, here we can assume this ABC is an isosceles triangle. This NDA moves to A dash and NDB move to B dash. And if we drop the perpendicular, here we can assume that theta remains constant. Theta remains same. So this side AC, the rod alongside AC is moved from C A dash. Therefore, the expansion of that rod AC should be equal to this A dash into M, and this expansion of this rod CB is equal to NB dash. NB dash is the expansion of this rod, and MA dash is the expansion of this rod, and expansion of this upper rod, AB rod, is AA dash plus BB dash, which are equal due to symmetry. So this is the expansion of this is the total expansion of that first rod. The expansion of this left rod, that AC rod, it is MA dash, and BC rod, CB rod is NB dash. Now from figure, cos theta can be written as, in the first case, before heating. From figure, before heating, cos theta can be written as, cos theta means adjacent side by hypotenuse. Median is of height h. Height of the triangle doesn't change here. Therefore, cos theta can be written as this adjacent side. The CD is the median height. That CD height doesn't change. Therefore, cos theta can be written as L1 by 2 by hypotenuse is L2 for this CBD triangle. Before heating. So you get L1 by 2L2. And after heating, from triangle AA dash M, cos theta, I will write it as, so here we have a right angle. So here we have right angle. Hypotenuse means AA dash. Adjacent side means A dash M. A dash M is the adjacent side, but A dash A is the hypotenuse. Therefore, A dash M is equal to A dash A into cos theta. A dash M is nothing but expansion of A dash M is nothing but expansion of rod AC. A dash M means expansion of half of expansion of AB, because so here either said that rod AB will expand. Assume it is riveted here. There is no free expansion at the C. They are riveted. Therefore, because that this point is not moving because the altitude is constant, the height of the triangle won't change. Therefore, A dash M is equal to A dash A into cos theta. A dash M means expansion of the rod AC, that is L2 alpha 2 into delta T, L2 alpha 2 into delta T, and A dash A, expansion of that rod, of the expansion of that rod, that is L1 alpha 1 into delta T by 2. L1 alpha 1 into delta T by 2. Cos theta we get it as L1 by 2L2. So both sides delta T get cancelled. 2 into 2 we get 4. We get 4L2 square. 4L2 square into alpha 2 is equal to, so L1 square into alpha 1. Therefore, L1 by L2 is equal, L1 square by L2 square is equal to 4 alpha 2 by alpha 1 Therefore, L1 by L2 is equal to 2 into root over alpha 2 by alpha 1. L1 by L2 is equal to 2 into root over alpha 2 by alpha 1. If it is equilateral triangle, L1 is equal to L2. Therefore, L1 is equal to L2, what we get? Alpha 1 is equal to 4 alpha 2. If it is equilateral triangle but made up of different materials. Two sides made up of one material and other side is made up of, third side is made up of another material. Therefore, alpha 1 we get it as 4 alpha 2. 4 alpha 2. Now, so there is a rod kept over the two surfaces. There is a rod is kept over the two surfaces that fixed. The ends of the rod is fixed. Kept over the surfaces or pivots. Assume it is thin rod. Assume it is thin rod. Assume it is thin rod. Now, kept over that surface. Here the length of the rod in equilibrium, it is given as L0. L0. Now, so given as some L0. On heating this rod, this is before heating. Before heating. After heating, so there is a buckle produced in the rod. Buckle produced in the rod means that the middle part is somewhat raised from that initial level. That from the initial level means buckle means it is about to break. about to break at that instant when the temperature is increased to some delta T. So this is very small height, y. After heating, then that y value we need to calculate. So about to break, it is about to break at that instant. So when the temperature is raised to some delta T, so then that y value we need to calculate. And y in the diagram. So you can assume what is the length of this rod, L0, initial length, final length we can say it is L and this is L. Total length is L if it is L by 2 and this is L by 2. Total length is L if it is L by 2 and this is L by 2. Now, so from the geometry of the diagram here we can say this is L0 by 2 and this is L0 by 2. So after heating, the length of the rod, half part if we consider, therefore y is equal to, from the diagram we can say y is equal to L by 2 whole square minus L0 by 2 whole square. L by 2 whole square minus L0 by 2 whole square. And where L by 2 is equal to initial length is L0 by 2 into 1 plus alpha delta T whole square. L0 by 2 into 1 plus alpha delta T whole square minus L0 by 2 whole square. L0 by 2 whole square. Therefore, y value here L0 by 2 whole square. L0 by 2 whole square or L0 by 2 by taking common or whole square by taking common. We get 1 plus alpha delta T whole square minus 1. It is 1 plus alpha square delta square 2 alpha delta T minus 1. As alpha is small, alpha square delta square is neglected when compared to 1. So alpha value it is on the order of 10 power minus 5 or minus 6. Alpha square term means it is very, very small. So 1 and minus 1 get cancelled. We get L0 by 2 into under root 2 alpha delta T. 1 get cancelled. This term is neglected. L0 by 2 into root over 2 alpha delta T. So if the numerical values are given, where alpha is the coefficient of linear expansion of that rod and L0 is the initial length of the rod, therefore that by what height it should be rise. That midpoint should be rise. By what height that midpoint should be rise, after heating, we can calculate.
Outfit వేసుకున్నా ఎవరు
Now, pendulum clocks. Now, pendulum clocks. So generally pendulum clocks are made up of inverse steel or metals. Therefore, on heating, as temperature increases on that day, they shows the wrong reading. So that's why to avoid that error in that time period, generally they made up of inverse steel, whose alpha value is very, very low. Inverse steel, whose alpha value is very, very low. So that's why we can prefer this material. We can prefer that material. We know the time period of oscillation of that pendulum, 2 pi root over L by G. Time period of oscillation of the pendulum, we get T is equal to 2 pi root over L by G. 2 pi root over L by G. Now, frequency of oscillation, we get 1 by T, and as T is proportional to root L, T is proportional to root L or L power 1 by 2, and F is equal to 1 by T. Now, generally, as temperature increases, as temperature increases, length of pendulum increases. Length of pendulum increases, time period increases, and frequency of oscillation decreases. Frequency of oscillation decreases. So here the pendulum clock says frequency of oscillation decrease means clock runs slow. Clock runs slow means it loses time. It loses time. Means as temperature increases, the pendulum clocks loses time. Oscillation decreases, frequency of oscillation increases, clock runs fast. Clock runs fast, so it gains time. It gains time. It gains time. So here, from the relative error method, if you want to calculate, T is proportional to L power 1 by 2. T is proportional to L power 1 by 2. So if for small changes in length, we write delta T by T is equal to 1 by 2 into delta L by L, where delta L by L is the fractional change in length. It is half alpha delta T. Delta T by T is equal to half alpha delta T. Half alpha delta T. So half alpha delta T. And the loss or gain of time. Loss or gain of time per day. Loss or gain of time per day, we can get it as a half into alpha into delta T into 86,400 seconds per day, 86,400 seconds. If we want to calculate the loss or gain of time per hour, we write here 3600 seconds. Per minute means 60 seconds. We need to multiply with 60 seconds. Delta T is the change in temperature. Delta T here, change in temperature. Now in method 2 here, the length, change in length is, change in temperatures are large. Your change in temperatures are small, we can use fractional error. If change in temperatures are large, we get T2 by T1 is equal to root over L2 by L1. L2 can be written as L1 into 1 plus alpha into T2 minus T1. 1 plus alpha into T2 minus T1 by L1. L1 get cancelled. Therefore, T2 by T1 we get it as 1 plus alpha into T2 minus T1 power 1 by 2. over 1 by 2. And from that, so fractional error, we can calculate by simplifying this value. So change in temperature by original temperature, we get T2 minus T1 by T1. T2 minus T1 is the change in time period by T1 is the original time period. Original time period. So like that, we can calculate by using that, we can calculate the loss or gain of time per day. If suppose now, for example, if the pendulum clock is made up of or calibrated at a particular temperature, calibrated means manufactured. The pendulum clock is manufactured at a particular temperature and doesn't give correct reading at any other temperature. Doesn't give at any other temperature. Now, if pendulum clock lose 5 seconds per day when temperature is 30 degrees Celsius, and the pendulum clocks gain 10 seconds per day when temperature is 15 degrees Celsius. 15 degrees Celsius. So then find the temperature at which it shows correct reading. And alpha of material of clock. Alpha of that material of that clock. Also we need to calculate. The pendulum clock loses 5 seconds per day when the temperature is 30, and again 10 seconds per day when the temperature is 15 degrees Celsius. Find the temperature at which it shows the correct reading and alpha of material of the clock. The alpha of material of the clock. Now we know that loss or gain of time per day, we read it as half alpha delta T into 86,400 seconds, that is per day. So generally, it loses the time in summer. It loses the time in summer. Summer means when the temperature is when the temperature is more than the calibrated temperature. Means as temperature increases, pendulum clock loses the time. Pendulum clock loses the time. And it gains the time when temperature decreases. So when temperature increases, it loses time. Means loses time means as temperature is increased beyond the calibrated temperature. Beyond the calibrated temperature. So here the pendulum clock shows the correct reading at some T degree Celsius. T degree Celsius. Therefore, delta T lose by delta T gain. The lose of time by gain of time is equal to calibrated temperature of the pendulum. We can say some T degree Celsius by when the temperature is increased, when the temperature is decreased less than the calibrated temperature, it gains the time. The temperature increased more than the calibrated temperature, it loses the time. So loss of time 5 seconds, gain of time 10 seconds, higher temperature 30 and lower temperature it is given as 15, which upon simplification 60 minus 2t is equal to t minus 15, because 5 2s are get cancelled, cross multiply that. We get 3t is equal to 75. Therefore, 3 equal to 25 degrees Celsius. Therefore, this is a calibrated temperature of the pendulum at which it gives a correct reading. At which it gives the correct reading. And alpha of that material can be calculated by using half alpha delta T into 86,400 seconds. It loses 5 seconds when the temperature changes from T to 30, that is 30 minus 25 into 86,400. Therefore, alpha is equal to 33 minus 25, 5 get cancelled, alpha is equal to 2 by 86,400. 2 by 86,400, that is 1 by 43,200 degrees centigrade inverse. 1 by 4300 200 degrees Celsius inverse. Like that, we can calculate the alpha value. Now, bimetallic strip. Bimetallic strip generally made up of two different materials are riveted together. So the thickness of that bimetallic strip is D and made up of two materials, alpha 1 and alpha 2. The length of that each material, each rod we can say L0 initially. Therefore, on heating, the bimetallic strip it bends. Here, assume alpha 1 is greater than alpha 2. This is before heating. After heating, it will bend. It bends. For heating, it bends. So the radius of curvature of that bended strip, initially it is straight, but it is bended by some amount. So the radius of curvature of that bended strip we need to calculate after heating. after heating. The radius of curvature of bended strip is that R value we need to calculate as D into, where D is the thickness of that strip, means each strip thickness is D by 2. We get 2 plus alpha 1 plus alpha 2 into delta T by 2 into alpha 1 minus alpha 2 into delta T we get. As alpha 1, alpha 2 are very small, alpha 1 and alpha 2 are very small, we have to neglect that this term. When compared to 2, this term is neglected because it is in the order of 10 power minus 5 or 10 power minus 6. Therefore, this term can be neglected. Therefore, we get 2D by 2 into alpha 1 minus alpha 2 into delta T, 2 to get cancelled. We get D by approximately D by alpha 1 minus alpha 2 into delta T, where delta T is a rise in temperature. Delta T is a rise in temperature of the rod. Now, metal scales and tapes. Generally, metal scales or tapes calibrated at particular temperature will not give correct reading at any other temperature. Will not give correct reading at any other temperature. So if the scale is calibrated at temperature T1 degrees Celsius, scale is calibrated at T1 degrees Celsius. Calibrated means manufactured, and is used to measure the length of an object, to measure the length of an object at T2 degrees Celsius at other temperature. So the measured length we can say it as some LM. T2 degrees Celsius. If suppose if T2 is greater than T1, then correct length, the length measured by that scale will be correct at T1 degrees Celsius only. But actually the scale is used to measure the length of an object at T2 degrees Celsius. Therefore, then correct length of object at T1 degrees Celsius is equal to, correct length is equal to measured length at T2 degrees Celsius, plus so expansion of that scale, expansion in divisions of scale. Here measured length is LM, So measured length of that scale is LM. In that LM length, whatever the number of divisions we have, so the divisions will expand when we use to measure the temperature at some other temperature as delta temperature rises to delta T. Therefore, correct length is equal to measured length into 1 plus alpha delta T we get. Actually, the body is correct at T1 degrees Celsius. T1 degrees Celsius. So at T1 degrees Celsius, it gives correct reading, but at T2 degrees Celsius, if you use scale expands. Scale expands. Therefore, the length of that object is measured at T2 degrees Celsius. Yeah, this one. So to get the correct length of that object, so we have to subtract the expansion of that scale in that length. So in the divisions, we have some number of divisions are there. So in that length, that number of divisions, the distance between the divisions, each division increases. Therefore, we have to subtract that expansion of that scale in that length, not entire scale. The expansion of the scale in this measured length, we need to subtract to get the correct length of the body at T1 degree Celsius. Therefore, correct length is equal to as the temperature expands, the reading given by that scale, here we can assume that body will not expand. Body is not expand now. Body is not expand. Assume because the body is some non-metal. Body is non-metal, but the distance between the divisions increases. If suppose this is a 5 centimeter mark, so now this 5 centimeter mark goes to this position. So therefore, the correct length can be calculated as measured length into 1 plus alpha delta theta. If T2 is less than T1, as temperature increases, correct length is equal to measured length into 1 minus alpha delta theta. Delta theta means here change in temperature you can take. Final T1 minus T2 you can take. Here and here you can take T2 minus T1. T2 minus T1, or you can apply any one formula, that is measured length 1 plus alpha delta T. As temperature increases, delta T positive. As temperature decreases, delta T you get automatically negative value. Suppose if object is metal. If object is metal, then correct length of that object. If object is metal, the correct length of that object we get it as correct length is equal to measured length into 1 minus alpha body minus alpha scale into delta T. Correct length of that body we get it as measured length into 1 minus alpha body minus alpha scale into delta T. So where Lm is a measured value at T2 degrees Celsius, measured value at T2 degrees Celsius, measured length at T2 degree Celsius. It is about metal scales and temperatures, metal scales and tapes, and thermal stress and thermal strain. Now, thermal stress and the strain. So when the rod is kept fixed between two supports, and the rod is kept fixed between two supports, on heating the rod, so it is prevent from expansion. On heating the rod, then it is prevented from expansion. Some compressive force will be created in that rod. Some compressive force will be created in the rod. Compressive force is created in the rod from either side. The rod is trying to push it or compress it. If L is the original length or L0 is the original length of the rod, L0 is the original length of the rod. So thermal stress developed in the rod, we can calculate it as here, if the length of the rod remains constant, if length of rod Young's modulus is y and alpha is the coefficient of linear expansion and A is the area of cross section of the rod. If length of the rod is constant, on heating, therefore compressive strain is equal to thermal strain. Compressive strain means change in length. Change in length delta L, we can write it as delta L is equal to, in case of elasticity, delta L we get it as YAE by L. F is equal to YAE by L, FL by AY. FL by AY, where L0 is the original length. And thermal strain we write it as alpha delta theta. Alpha delta theta, where delta theta is the rise in temperature of this rod. As temperature is raised by delta theta degrees Celsius. So FL0 by AY into alpha delta theta. So strain means L0 is not there. Strain means L0 is not there. Just stress by Y, F by AY. F by A is known as thermal stress. Thermal stress is equal to F by A, that is equal to Y alpha delta theta. Y alpha delta theta. So thermal stress we get as Y alpha delta theta, and thermal strain means here when the rod is trying to expand, but at the same time, due to expansion, it exerts a force on the walls and wall exerts a force on the rod. Therefore, it trying to compress. So due to this compressive strain should be balanced by that expansion due to heating. That is known as thermal strain. Therefore, thermal stress developed in the rod is equal to Y alpha delta theta, and compressive force. Compressive force F is equal to, we get YA alpha delta theta. Compressive force we get as YA alpha delta theta. YA alpha delta theta. If suppose if two rods are joined in series, it is also given in elasticity, or may here the two rods are riveted together between supports. If length of that each rod we can say L0. Length of the each rod is L0, and Young's modulus of the rod is Y1 and Y2, and alpha 1 and alpha 2 as the coefficient of linear expansions. Area of cross section of the each rod is A. Each rod is A. So on heating, each rod will experience a compressive force. On heating, so each rod will experience a compressive force. This is the junction. This is the junction. Now displacement of the junction we need to calculate on heating. On heating, so displacement of the junction we need to calculate. Displacement of junction displacement of the junction on heating is on heating the rod, the displacement of the junction. Here we can assume that composite rod the length of the composite rod remains same. It is kept between two supports. One rod expand, another one. One rod is expand, another one is compress. So here initially the junction will be here. Now the junction is displaced to some other point. Here we can say this is a junction now. It is displaced by an amount x. Therefore, this length becomes now L0 plus x. This length becomes L0 minus x. But here original length of the rod that remains same 2L0 because they are fixed between two supports. Then, or if you can assume for simplicity, if you can assume these are L1 and L2. So this is L1 plus x and this should be L2 minus x you get. L2 minus x you get. Therefore, what is the compressive strain in the first rod? Compressive strain in the first rod. Strain in first rod. Compressive strain in first rod. Here actually we can say it is junction is at B. It is finally set at C. Actually on heating, so that first rod is expanded to BD and again due to compressive force it is come back. So it is compressed by DC. Therefore final change in length of that rod, give it as BD minus compressive strain, we get it as BD minus BC. BD minus BC by original length is L1. BD is nothing but expansion of that rod and the BC is nothing but a displacement of the junction by L0. And similarly, compressive strain in second rod. The compressive forces are acting on that first rod and as well as second rod, due to which how much it will compress. Second rod is equal to, we can assume it is E. Actually the junction, the length of the rod initially is L2. Now it is moved towards left by an amount E, but finally it sets at C. Therefore, expansion due to heating it is BE, and finally it set at position C. Position C means it is again come back. It is again come back to that position, that C. So that is due to compression. It is displaced from E to C, and due to expansion it moved from B to E. Therefore, the final compression we get as BE plus BC is the final compression of the rod. Therefore, initial length it should be L2. BE means elongation due to heating. We get L2 alpha to delta theta plus x by L2 plus x by L2. So that is the compressive strain produced in the two rods. Now here the compressive forces acting on both ends is same. Compressive forces F1 is equal to F2. F we know that Y1 into A into strain produced in that rod, we get it as L1 alpha 1 delta theta minus X by L1. And compressive force acting on the second rod Y2 into A area of cross section of the rod is A into L2 alpha 2 delta theta plus X by L2. This L2. Now, here A get cancelled. After rearranging the terms, we get X value. After rearranging the terms, we get X value like this. X is equal to Y1 alpha 1 minus Y2 alpha 2 into L1 into L2 into delta theta by Y1 L2 plus Y2 L1 is the displacement of the junction. Displacement of the junction. If L1 and L2 are equal, some L0, X value we get it as Y1 alpha 1 minus Y2 alpha 2 into L0 into delta theta by Y1 plus Y2. Y1 plus Y2. And this concept may link it with rotational mechanics. From rotation, we know that angular momentum L is equal to I omega. On heating, L is constant. So on heating, I value increases, omega decreases. On heating, a moment of inertia increases because due to increase in length of the rod or due to increase in radius of that rotating object. So in case of rod, length of the rod increases. That's why moment of inertia increases. Moment of inertia increases. Omega decreases. Angular velocity decreases. Therefore, as we know that I is proportional to L square or I is proportional to R square, therefore delta I by I is equal to 2 into delta L by L, or delta I by I is equal to 2 into delta R by R. For fractional change in radius or fractional change in length, we use alpha only. Alpha only we use. So 2 alpha delta theta. Delta I by I is equal to 2 alpha delta theta. Now, So here, when compared to omega, when related to omega, as I is inversely proportional to omega, delta I by I can be written as minus delta omega by omega, that is 2 alpha delta theta. So the decrease in angular velocity or fractional decrease in angular velocity we get from this relation. So that the temperature effect on moment of inertia of a rotating object or angular velocity of that rotating object. And variation of that density of the solid with the temperature for a liquid and solids, variation of density will be remain same for both solids and liquid. For both solids and liquids, both solids and liquids, as temperature increases, volume of the liquid increases or a volume of the solid increases, density decreases. As density is equal to mass by volume, as mass of the body is constant, so ρ1 by ρ2 is equal to V2 by V1. Final volume we write it as 1 plus gamma into delta T by initial volume. Therefore, we get it as 1 plus gamma into delta T. 1 plus gamma into delta T. Ρ1 by ρ2 we get it as 1 plus gamma delta T. Therefore, ρ2 is equal to ρ1 by 1 plus gamma into T2 minus T1. In case of liquids, in place of gamma, we have to take real expansion of the liquid. Real expansion of the liquid we have to consider. And if ρ0 and ρ3 are the densities at 0 and T degrees Celsius, or densities at 0 and T degrees Celsius, so ρT is equal to ρ0 by 1 plus gamma T. Density at T degrees Celsius is equal to density at 0 degrees Celsius into 1 plus gamma T. Like that, as temperature increases, density of the solid changes or density of the liquid changes. Now, expansion of liquids. So we have only few applications on expansion of the liquids. We know that liquids doesn't have any shape and size. So they occupy the shape of that container, and they do not have definite shape. They occupy the shape of the container. Therefore, on heating the liquid, so it expands. So before expansion of that liquid, solid also expands, because that liquid is taken in a container and then it is heating. It is taken in a container and then it is heating. Therefore, on heating that liquid by taking in a container, so first solid expands and then liquid expands. First solid expands and then liquid expands on heating it. So we define two coefficients of expansion for that liquids. One is expansion of the liquid with respect to container. Expansion of liquid with respect to container. And another one is real expansion of the liquid. Real expansion of liquid. This is known as apparent expansion. Apparent expansion. So apparent increase in volume is equal to gamma A into initial volume into delta T. And the real increase in volume can be calculated as gamma R into V into delta T, where V is the original volume, and gamma A and gamma are the coefficient of apparent expansion and coefficient of real expansion of the liquid. Coefficient of apparent expansion and real expansion of the liquid. And Vi is the initial volume of the liquid. Coefficient of apparent expansion of liquid. And gamma R means coefficient of real expansion of the liquid. Coefficient of real expansion of the liquid, which depends on nature of liquid and the nature of solid. Nature of liquid and solid. And depends on nature of liquid only. Real expansion depends on nature of liquid, is independent on the vessel nature in which that is heating. It is independent on the vessel nature, so it is depends only on the nature of the liquid. But apparent expansion, coefficient gamma A value depends upon so nature of the liquid and as well as solid. Nature of the liquid and solid. So we can relate gamma R and gamma A as relation between them. Relation between gamma A, gamma R. Is gamma R is equal to gamma A plus gamma Z. Gamma R is equal to gamma A plus gamma Z. This gamma R is equal to gamma A plus 3 alpha Z. Gamma R is equal to gamma A plus 3 alpha Z. Gamma A plus 3 alpha Z. That is the relation between gamma A and gamma R. If same liquid is heated in different vessels, gamma A value we get different, but gamma R is same. Gamma R value is same, but gamma A we get different values. Same liquid is heated in different vessels. if same liquid is heated in different vessels, gamma R is same. Gamma A we get different. Gamma A1 plus 3 gamma Z1, sorry, 3 alpha Z1 is equal to gamma A2 plus 3 alpha G2. Where alpha G1 and alpha G2 are coefficient of linear expansions for the two solids, two different vessels. In two different vessels, for that alpha 1 and alpha 2 are the coefficient of linear expansion for that two vessels. Now, if gas liquid is taken in a container, if volume of empty space above the liquid is same at all temperatures, volume of empty space above the liquid is same at all temperatures, therefore real expansion is equal to, real expansion of liquid is equal to cubical expansion of vessel. Cubical expansion of vessel. That is gamma R into initial volume into delta T. That is the volume of the liquid into delta T is equal to gamma Z into volume of the glass vessel into delta T. So from that we can calculate gamma R into volume of that liquid is equal to volume of the glass vessel into gamma of the glass vessel into volume of the glass vessel. So if gamma real expansion of that liquid and gamma Z or alpha value is given, gamma Z we write it as 3 alpha Z for solid vessel. So if alpha is given, we can calculate gamma as 3 alpha, we can substitute here. This is the volume of that glass flask and VL is the volume of that liquid. Volume of liquid taken in container, and this is the volume of glass vessel. Volume of glass vessel. Now, when the expansion of the solids, liquids is related to fluid mechanics, here what is the volume of empty space? Volume of empty space means volume of the glass flask minus volume of the liquid taken in the glass flask. That empty space volume is constant at all temperatures. For this to be happen, so this is the required condition. Now, effect of temperature on buoyancy. Temperature on buoyancy. So here we know that if a body is partially or completely immersed in a liquid, then force of buoyancy at a T1 degrees Celsius, if you want to write, force of buoyancy we read it as volume of the solid which is inside, volume of the body which is inside, we can take it as V in into density of the liquid, we can say sigma Z, and at a T2 degrees Celsius, volume of the body inside, we can say V in dash into sigma dash into Z. Therefore, force of buoyancy, FB by FB dash is equal to volume, initial volume inside by final volume inside into density of the liquid at T1 degrees Celsius by density of the liquid at T2 degrees Celsius. So which upon simplification, we know that final volume can be written as initial volume into 1 plus gamma delta T. Therefore, 1 plus gamma solid into delta theta And here we rate, so density of the liquid we rated as initial density by 1 plus gamma liquid into delta T, plus gamma liquid into delta T. 1 plus gamma L by delta theta by 1 plus gamma S into delta T we get. Generally, expansion of the solid is less than the expansion of that liquid. Gamma S is less than gamma L. Gamma S is less than gamma L. So FB dash is less than FB. Means as temperature increases, if T2 is greater than T1, means as temperature increases, which is greater than T1 degrees Celsius, buoyancy force decreases. Buoyancy force decreases. Then apparent weight. Apparent weight of a body can be measured as apparent weight is equal to true weight minus buoyancy. Apparent weight is equal to true weight minus buoyancy. Force of buoyancy. Now, as temperature increases, buoyancy force decreases. As temperature increases, buoyancy force decreases, therefore apparent weight increases. Apparent weight increases. Now, in this case, fraction of volume submerged. In case of floating, fraction of volume submerged. Fn is equal to volume inside by original volume, that is equal to, so volume inside by original volume, we get it as density of the solid by density of the liquid. Density of the solid by density of the liquid we get. Therefore, at T1 degrees Celsius, fraction of volume submerged is F1, rho S1 by rho L1. At T2 degrees Celsius, fraction of volume submerged is rho S2 by rho L2, where the rho S2 and rho L2 are the density of the solid and the liquid at T2 degrees Celsius. Therefore, the ratio of fraction of volume submerged at T1 and T2 degrees Celsius, we get it as 1 plus gamma S into delta theta by 1 plus gamma L into delta theta. 1 plus gamma L into delta theta. So, there are some cases when related to that fluid mechanics. So, you can go through that expansion of solids and liquids. Did that expansion of solids and liquids by tomorrow. Is it clear?
Yes, sir.
And all of you maintain these short notes. All of you maintain these short notes. Keep with you for the final preparation. So these are the key points and important problems. Some problems we can discuss. And tomorrow we can see calorimetry and heat transfer. Wednesday kada Wednesday calorimetry heat transfer complete aithe, Thursday Friday thermodynamics KTG. Okay, I'll close the session now. Anybody have doubts? Yesterday problems we are doing. Problems చేశారా?
Yes, sir. కొన్ని
ఓకే, డౌట్స్ ఉంటే మెసేజ్ పెట్టండి, స్టడీ అవర్లో డిస్కస్ చేద్దాం. Otherwise, I will send an assignment and go through that.